RM Karp series to celebrate the pioneering role of Simons Institute founding director Dick Karp in theoretical computer science. And we're grateful to the many contributors to the Richard M. Karp Fund who've made this series possible. The series features visionary leaders in the field of theoretical computer science on topics associated with current programs running at the Simons Institute, and it's geared towards a broad scientific audience. So this semester, the Simons Institute is hosting 2 online programs, one on probability geometry and computation in high dimensions, and one on the theory of reinforcement learning. And I'm delighted to welcome our speaker today, Professor Dale Schuurmans, who's participating in the program on the theory of reinforcement learning. Dale's a research scientist at Google Brain and Professor of Computing Science at the University of Alberta in Edmonton. I've had the pleasure of knowing Dale for 25 years now. He's famous for his work across a range of areas in machine learning and AI, including reinforcement learning, online learning, Bayesian optimization, and unsupervised learning. He's received paper awards at NeurIPS, ICML, IGCAI, AAAI, and he's had a 10-year Canada Research Chair in machine learning. And Dale's a fellow of AAAI. Today, we're delighted to have him present a talk entitled Reductionism in Reinforcement Learning. Welcome, Dale.
Thanks, Peter. Thanks for giving me this opportunity to present to you today. Before I get started, I do want to acknowledge the many collaborators that are actually responsible for most of the results behind what I'm going to try to explain today. Most of these collaborators are based at the University of Alberta, Google Brain, and also some at DeepMind. Okay, so my focus in this discussion is going to be about reinforcement learning, but I'm going to share a little bit of an idiosyncratic perspective on this field. This is now my 3rd independent attempt to try to make sense out of reinforcement learning. So I want to start with this holistic view. So when you enter the field of reinforcement learning, you're probably quickly confronted with this picture, which is we pose the problem as solving this agent environment interaction task, where there's an agent, it takes actions, it affects the state of the environment, receives feedback in the form of observations and rewards. I actually find this picture highly problematic for the simple reason that it makes simple what is not simple. It hides many, many complexities behind this simple diagram, having to do with the nature of the environment and also the agent's access to that environment. Moreover, one quickly finds the field seems to be dominated by what I will call this kind of update-based algorithmic approach, where in synchronization with this experience loop, we're going to learn or plan in this kind of synchronous update kind of manner. I've just found it personally very difficult to make progress with this kind of holistic approach to the problem. So what I want to try to do a little bit is advocate a bit for a more reductive perspective. So another way to think about the reinforcement learning problem, again at a high level, is to think about it, quite simply as learning decision-making interactively, but to recognize that there are many sub-problems and many sub-fields involved in this pursuit. For example, we could just start by focusing on decision-making itself, which is a very important problem studied, in many areas of computing science and engineering under the rubric of optimal control theory, decision theory, so on and so forth. And there's a very rich hierarchy of problem types there, and a diversity of solution concepts, and a lot of profound algorithmic achievements and insights in solving decision making, which we normally express as a planning problem, where we're given a model and we're just trying to compute like an optimal search algorithm or a compiled decision strategy. Now, reinforcement learning is indeed more ambitious than that. We are, in addition to trying to solve something like an optimal decision-making task, we're trying to do it on the basis of not having the model known ahead of time. So instead of a model, we get data, in the form of experience, like, observation, action, reward, next observation, experience sequences. Still given data, we can think of the problem as a learning problem where we could, for example, reduce it to decision making by extracting a model from the data and then applying algorithmic concepts from optimal decision making, or this very interesting possibility of bypassing model construction and going straight to trying to infer compiled solution concepts in the form of a reactive policy or a value function. But reinforcement learning is even more ambitious than this. It doesn't just consider the problem of learning decision-making from a fixed set of data. It actually considers the full loop where we're also responsible for collecting the data that we then use to infer solution concepts. And this loop here is the corresponding to that simple agent environment interaction. But from this perspective, I think one can appreciate that there's a significant amount of complexity behind the overall problem, with many variations and many subproblems involved. So by taking a reductionist stance, what I mean to say is I've personally found it much more productive and meaningful to not take on the full loop or the full problem in one whole swoop. Instead, it seems to me that I've found more understanding in picking off and isolating subproblems of the overall picture. And so my plan today is just going to be to share with you a couple of recent works, actually, where we've made progress in understanding a couple of the, I think, key subproblems. The first part of the talk, I'm just going to focus on some recent work, which might seem quite unambitious, but is going to focus on the batch single step decision-making problem. And there, quite remarkably, I would say that in the last 2 years, there's been amazing progress. It's actually quite stunning that we're still learning an awful lot about this very basic core problem in reinforcement learning. Once I finished that part, I then am going to switch gears a bit and also try to share some yet even more recent work on understanding some basic issues in learning in a sequential decision-making context, primarily focusing on how we're managing the reasoning horizons. Okay, so let's start by considering the single-step decision-making problem. Quite simply, what we're interested in here is taking a collection of data, which I'm representing as a simple matrix, and inferring a policy from this data that we hope works well on future data. To be a bit more precise, let's imagine our data is given to us in this kind of contextual bandit-like format, where we have a set of contexts, x1 to xm, that have somehow been measured. Say, for simplicity, a finite set of actions, a1 to an, and our data consists of, there was a context, an action was taken, and a reward was recorded for that action in that context. Therefore, in context x1, we took action a2 and we observed reward r1, for example. And our goal is to process this set of data and to produce a policy. A policy here is going to be simply a map from context to a probability vector across actions, denoted by pi. And we're going to work with a pretty typical parameterization of policies, where instead of actually directly learning the policy, what we're going to be concerned with is learning what I'll call a score function here, occluded at the bottom there. A score function Q, which for a given context emits a score across actions, which is then converted to a probability distribution by exponentiating scores and renormalizing, otherwise known as the softmax transfer, which we'll deal with later. So our task is quite simple. Take this data, optimize the parameters of a score function that when converted to a policy, has a high probability of choosing good actions, or more precisely, achieves high expected reward, not just on this training data, but more importantly on future test contexts. Although it's somewhat simple to set this problem up, it turns out there are many profound difficulties from an algorithmic and inference perspective when trying to solve this problem. And I want to focus on two subproblems here. The first subproblem I'm going to talk about is an even further simplification, where we just consider the optimization or the training task associated with this kind of parameterized policy data optimization setup. And then I'll back up a bit and then reconsider how we might deal with missing data here. So first, to focus on the optimization problem. To make things simple and to isolate this task, I'm going to temporarily assume that we have complete data. So this is not very realistic, but imagine instead of just sparse data, we have this kind of counterfactual data collection, where for each context, say x1, we have counterfactually gone back and tried every different alternative action in this context and recorded the reward that you would have gotten if you'd taken this action in that context, and build a complete training table over a finite set of contexts, more like a supervised learning setup, where in fact we could even assume high ID contexts. Now, this does seem like a simple setup, and we could target a very natural and straightforward objective, which is if we're trying to extract a good policy from this data, we would formulate the natural objective, which is let's optimize over the policy parameters or the score function parameters, simply the expected empirical reward, the average reward that that policy would achieve on this data. And this seems pretty cut and dried. It seems like, you know, we've got a coherent objective, it's differentiable, we could just do gradient descent and descend our way to victory. Turns out, however, that this is a very challenging task, which is actually at the heart of reinforcement learning. You know, it's easy to lose sight of this core task when we look at much more elaborate scenarios, but it's sitting there at the heart. And yet it turns out that this objective has particularly serious problems from an optimization perspective. Maybe to reveal some of those difficulties, if we just dig in a little deeper, we'll notice that actually what we're trying to do is optimize the parameters of the neural network, which is emitting the score vector across sections. So we're really optimizing this middle objective, which is R dot softmax transfer of scores. This interaction of the dot product between the rewards and the softmax transfer is actually very problematic from an optimization perspective. Most serious problem is that it creates plateaus. If you exaggerate a score on a particular action in a context, the softmax transfer saturates, and you wind up getting gradients that are near zero. In fact, the optimization landscape has near zero gradients almost everywhere. Even potentially worse than that is that if your score function parameterization is undercomplete in any sense, that is, you're not able to span arbitrary policy vectors across all contexts, so you have some trade-offs to make, then you can quickly find yourself in a situation where, from the perspective of the parameter optimization, there are exponentially many local maxima in the optimization landscape. In practice, what this simply means is that it's nearly impossible actually to directly optimize this objective and find a good solution, even not even a near optimal solution. Okay, but the point I want to make here is what's interesting about this task is that we actually know in other areas of machine learning and statistics that this is not a fruitful approach. And in fact, the default approach to this problem in other related areas is quite different than directly attacking the expected reward optimization problem. In fact, I would argue that most people on this call, if you've had any sort of course or prior experience in machine learning, you've no doubt learned about supervised learning. You've already encountered a scenario where you have had a problem like this posed to you, but you've solved it in a different way. To make this clear, I'm going to specialize the problem a little bit temporarily, let's just imagine for the sake of argument that the rewards in that reward table are simple 0-1 indicators where we have a single 1 in each row. This is isomorphic to a supervised classification problem where that 1 is indicating the correct label or action for the context or the input example. For that kind of indicator reward function, expected reward is nothing but expected accuracy. So we do indeed care a lot about expected accuracy. We would like to maximize the expected accuracy of the policy on future test data. But I'll just remind you that when you're confronted with this problem in a supervised learning context, even though you cared about expected accuracy, you did not optimize expected accuracy when you're training the parameters of the model. Instead, what you inevitably optimized was maximum likelihood. Log likelihood, or put more plainly, instead of maximizing R dot pi, you maximized R dot log pi. This is actually a very important concept, which we just presume by default in supervised learning, but is somehow a lesson that is less prevalently appreciated in reinforcement learning. What's going on here? Well, the fact is we do care about accuracy. So often in supervised learning, you do indeed measure like misclassification error on training data and misclassification error on test data. But we don't train by directly trying to minimize misclassification error. Instead, we train by maximizing likelihood. The reason for this is quite simple is, well, two reasons. One is the r.log_pi objective still shares an important relationship to the r.pi objective. In particular, for any target value in r.pi, there will always be some target value in r.log_pi for which the solution achieves that desired target value in r.pi. Or put another way, this proxy objective or surrogate objective, maximum likelihood, is calibrated with respect to the original objective. In addition, the maximum likelihood objective is now convex, or sorry, concave from a maximization perspective, concave in the score vector emitted by the neural network. This essentially is like taking a very difficult plateau riddled and possibly local maxima riddled objective and building a concave proxy objective that's centered at the peak. This is so effective, in fact, that in practice, this is all we consider in supervised learning. Now, if we just take this back to our general reward case, we really still are thinking about a supervised learning problem, which is known as context-sensitive classification. And the goal here would be to essentially generalize maximum likelihood to a more general class of surrogate objectives that allow us to deal with arbitrary rewards, not simple indicator rewards. There has been work on developing calibrated surrogates for this objective in the cost-sensitive classification setting. There's remarkably not a large literature on this, and I would say that some of the results are recent-ish. But nevertheless, the problem has been posed before. What I want to just advocate for a little bit is a very interesting systematic way to develop surrogates in an intuitive manner that's actually related to maximum likelihood. And the simple way to do this is by introducing a small amount of entropy regularization. So one could imagine taking expected reward as the target objective, but just adding, tau, some temperature parameter times entropy of the policy as a regularizer for the optimization. Now, entropy regularization by itself does not really mitigate the problems. It simplifies the landscape a little bit. It does accelerate training, but it actually doesn't really achieve the same kind of benefits of maximum likelihood. However, once we express the entropy regularized expected reward objective, we immediately find an interesting mathematical structure that we can exploit. In particular, entropy regularized expected reward maximization is isomorphic to minimizing a KL divergence between your policy output and an implicit target distribution P, where the implicit target distribution P is defined by exponentiating the reward vector, perhaps pre-scaling it by a temperature parameter tau, and then normalizing. What's interesting about this setup, well, there's many reasons why it's interesting, but one of the key things that's interesting about this is it sets up a relationship between a score vector and a policy probability vector and a reward vector and a target distribution vector. So we get this kind of duality where we can simultaneously think in the score or reward space or the policy and probability space. I'll come back to this later. Entropy regularized expected reward maximization is nothing but minimizing the KL divergence in the mode seeking direction, minimizing the KL of pi and p to this implicit reference distribution p. Once we're looking at KL divergence minimization, there's now a completely natural and obvious way to generate a concave surrogate objective simply by considering the reversed direction of the KL, which goes from a mode seeking to a mode covering orientation. The reversed KL now is an objective that is, as before, convex in the score vector, the output vector of the neural network. And calibrated in the sense that we have preserved the global minimizer of the entropy regularized objective. This shares some nice relationships to the maximum likelihood objective. In fact, you could see it as just a natural generalization of maximum likelihood. I'm going to actually just push a little bit further in a slightly different direction, as it turns out that once we're thinking about convex calibrated surrogate objectives to a target objective, entropy regularized expected reward, there's a whole space of possible surrogates, not just based on KL divergence, but perhaps also based on quadratics and so on. What's interesting here is that you can actually think of composite surrogate objectives that bring together many parts, all of which are convex and calibrated. And you can, in addition, achieve an upper bound, so a convex calibrated upper bound on the target objective that nevertheless preserves the location of the global maximizer. This is very useful in theoretical arguments about showing that minimizing, say, an empirical version of this convex upper bound will eventually imply achieving a good target objective. I won't spend too much time dwelling on experimental results in this presentation, but it turns out this is actually a pretty reasonable way to develop useful training objectives, even in supervised learning, that in fact do allow you to achieve some advantages over naive maximum likelihood. And one reason why we even see advantages, not just in training optimization, but in test generalization, has to do a little bit with this generalized KL doing an implicit form of label smoothing. But I want to move on to another, I think, more surprising and more recent observation when we consider the problem of maximizing expected reward. And that's to actually go back to the beginning and reconsider the role of the softmax. Now, I'll remind you that the softmax transfer itself is, in a way, the key source of optimization difficulty, even when we're targeting what we declare as the target objective. Excuse me. So all of the results I just shared with you didn't question the use of the softmax, but instead committed to the softmax and instead just built proxy surrogate objectives for the training target. However, we can go back to the original expected reward maximization problem and reconsider the role of softmax. And here it's actually quite shocking, I think surprising, that there's actually been some very recent breakthroughs, just in the last year, in fact, in understanding the nature of directly optimizing expected reward. Agarwal et al. Within the last year have discovered that just simple gradient descent optimization of this objective actually remarkably does find a global maximum, even though this is a non-concave maximization, in the case of a tabular score function. We've recently strengthened this result to actually put rates to establish both upper bounds and lower bounds on the rates of convergence of gradient descent in this setting. And all of these results are indeed generalized far beyond just sort of tabular settings to, contextual bandit settings and even general Markov decision processes. But what I want to acknowledge is somehow this seems like a direct contradiction to what I started out saying, is that this is a problematic objective and we should reformulate it in terms of surrogates. Well, what's going on here is that indeed, simple gradient descent in the overcomplete setting will eventually find a global minimizer. And we even have rates, upper bound rates, giving 1/t rates of convergence of gradient descent to a global maximizer. But what those bounds are hiding is specific constants. And it turns out that the big O, like the 1/t upper bound, hides not only just problem specific constants, but initialization specific constants. So the real reason why training to maximize expected reward in practice is almost hopeless is that eventually you can, with enough capacity in the neural net, eventually you can get to a global maximizer, but we don't have good enough ways to initialize the parameters of the network to avoid these bad cases. And you can show that theoretically for any problem setup, there always exists some valid initialization that keeps the results of gradient descent optimization strictly suboptimal for an arbitrary long period of time. That is, for any problem setup R at any time horizon T, there always exists an initialization that keeps you far from optimality up until at least T time. In practice, what we see is when you look at gradient descent minimization or maximization of this objective is that it is strongly attracted to suboptimal corners of the simplex. And once it gets near a suboptimal corner, eventually it will escape, but it takes astronomically long amounts of time to escape. And it's very difficult to avoid these initialization traps with the softmax transfer. In response to this, actually, another recent discovery is to question, like, well, why are we just committed to the softmax? So it's true we understand that this is like in every code base in machine learning around the world right now. And there are many historical reasons that motivated that as a reasonable mapping from an arbitrary score to the probability simplex. But of course, it's not the only one. Once you think about the problem of reformulating a mapping to the simplex, there are entire families of continuous smooth mappings that can map score vectors to simplex. And so just as a simple investigation, we considered an obvious polynomial transfer. So instead of exponentiating scores and normalizing, you can imagine just raising scores to some power, absolute value, and normalizing that, and mapping that to a policy. This mapping has been actually studied in physics under the name of S-score transform, and it's also appeared sporadically in the machine learning literature. What's interesting about this, though, is we found that just replacing the softmax transfer with this kind of softer polynomial transfer actually yields not just empirical but theoretical benefits. So one simple result is that if we replace softmax with the polynomial, okay, we still get an O1/T rate of convergence, but now we can establish that convergence with an initialization independent constant. That is, we can mitigate the initialization sensitivity of softmax, expected reward maximization, profoundly by just replacing the softmax. And what's also interesting is we see empirically, both in simple like Bandit all the way up to MDP contexts, that this modification renders huge empirical benefits, certainly in terms of the speed of training or the speed of optimization. I find it actually quite surprising that just now we're finding these very basic facts about the nature of the optimizations that we're attempting way down in the central core of reinforcement learning before we're even dealing with like exploration and missing data issues. Okay, so I now want to pivot to missing data just briefly. Now I may try to save a bit of time here. Okay, arguably everything I've just talked about, isn't really reinforcement learning. Often I'm criticized and it's declared to be supervised learning, fair enough. We could look at missing data maybe as the key distinction between a supervised and reinforcement learning setup. That is, in supervised, we assume we see counterfactual reward observations for every action in every context, or in an infinite action setting like regression, we presume that we have a score function that allows us to compute for every action what the loss or cost would have been for that action in any context. We're now going to consider how do we cope with missing data where we've only logged a very sparse subset of reward observations for a subset of actions. And most practically, really, we only ever log a single action in a given context and record what the reward was. We rarely go back to the same context twice and counterfactually check what an alternative action would have achieved. Okay, so missing data is prevalent. It's a very core issue in reinforcement learning, and yet reinforcement learning tends not to take the problem as seriously as other areas of machine learning and statistics, but still has made some progress. So I just want to characterize maybe a simple way to deal with missing data, but it winds up being essentially the default way of dealing with missing data that's still prevalent in reinforcement learning. And by this, I mean taking an imputation strategy. That is, we might imagine one confronted with this table of incomplete data, that the first thing we could do is simply complete it by having some model or using our score function to fill in all the missing data for us, reduce the problem to now a fully observed problem, and then we can apply like the previous optimization techniques for the purposes of training. Despite the naivety of this, this actually is a technique that's sort of at the core of default reinforcement learning approaches. To make this a little more clear, let me highlight importance corrected expected reward maximization as sort of a default representative of this class of missing data techniques. Now, importance corrected expected reward is actually an imputation strategy. It's mathematically equivalent to taking that original sparse set of data and imputing a 0 for every unobserved reward, and then taking the observations that you do have, the rewards you do see, and altering those. In fact, exaggerating those by the proposal probability beta. Now, we will notice here that this rescaling of the rewards does require us to know the probabilities with which the particular action was chosen in that context. Usually in practice, if that's not logged, what you will do is you'll fit like a maximum likelihood estimator of the behavior, like the action sampling process, and then use those estimates as the propensities or the proposal probabilities. Regardless, we can see that this is actually a fairly ham-fisted and egregious way to complete the data. It makes no attempt to make good guesses about what the missing rewards are, and exaggerates quite profusely the observations we do have. Why would anyone consider this? Well, the main motivation for this is, despite its kind of extreme nature, it is an unbiased estimate of the expected reward objective. That is, if we consider the sampling process, we draw a particular action according to the sampling process in each context. Well, the estimated reward vector is a one-hot vector with an exaggerated reward on that single entry. But if you average that over the sampling process, you can quickly see, it's a simple one-liner, that in fact you get the expected reward vector that you estimate is indeed the correct expected reward. So it is an unbiased estimator, but it's actually quite clearly unsatisfactory. More reasonably, in practice, right, people will consider what's called a doubly robust estimator, which is actually just a one-step deeper version of importance correction, where instead of just filling in the missing data with zeros, we'll fill it in with a model guess. So assume we have a model, some score function Q, and we use it to complete the rewards. Then on the observed data, to preserve unbiasedness, all we're going to do is exaggerate not the reward itself, but the delta, the discrepancy between the reward and the model guess. And an argument basically identical to the previous can show that this yields an unbiased estimate of the reward vector still for an arbitrary model guess Q. Now, this is a significantly more effective approach, but it does raise some questions. The main question it raises is, where should the model come from? Now, there's a bit of a subtlety, which is the unbiasedness argument technically requires the model to be independent of the data. So if we dare estimate the model from the same data, we do actually lose a perfect unbiasedness argument. In practice, though, I'd say that this creates another problem that I want to close up. So it's typical in in reinforcement learning to think about policies and value functions or scores or rewards as somehow living in a different space. They're serving a different role. We should therefore think of them as separate models. So a natural way to approach this is, even when we want to optimize a policy pi, that we should temporarily hold pi to the side and just directly try to learn a good model of value or reward. Take that model that we've learned, perhaps just least squares regression to the target rewards, and take that model, now treat it as a proxy, essentially a completed data set, a proxy for the real reward function, and then optimize the policy to that. Now, in this setting, we can see that approach is actually quite ineffective for a simple reason. First, that when we say do something like a least squares regression to the rewards, if we don't correct, we're technically biased. But also the policy optimization becomes obviated. It's literally just taking that score function and doing the argmax. So essentially that argmax is a stronger version of the softmax transfer of the score function. So we're really just learning a score function by least squares, which we've seen in the previous context, at least briefly in some of the plots that ran by, is that that's actually not very effective. What's often overlooked here, though, is that I think there is a more satisfactory way to approach and think about this problem. And it's to harken back to when we're looking at optimization objectives and surrogates, and in particular based on the KL divergences, to recognize that there's actually a way to unify policies and scores, or rewards and target distributions. And instead of thinking of everything in the probability space as a separate model for everything in the score space, we could actually think of them as connected by a transfer, say here like softmax. And we could think of one model that simultaneously serves both roles. It can be interpreted as a score function if we're looking at it before the softmax transfer, or a policy if we look at it after the softmax transfer. This unified view actually is really useful here, because now it allows us to not think of this separate actor-critic where we're kind of locked in place with a very crude relationship. We can now train the policy in a way that's directly informed by how the score function is relating to the rewards. And in addition, we can simplify the optimization by using the previous surrogate objectives to render more congenial optimization landscapes. So in a nutshell, you can combine these two parts of the study into a single objective where we simply replace the implicit target distribution with an inferred target given by, say, a doubly robust estimate extracted from our model. But it's still just an optimization which allows us to minimize some convex upper bound on a target objective. Okay, it might seem like bringing a lot of pieces together and a little bit unprincipled, but actually, I'll just skip ahead here. This combination is technically sound in a certain sense. That is, one can show by combining the previous results showing that we have a convex upper bound, convex calibrated upper bound, combined with this imputation process, that these two things don't interfere. And one can show that indeed, if you're able to achieve a small empirical surrogate risk using one of these upper bounds, that will imply with high probability a small true risk. Under some nice technical assumptions, but pretty generic technical assumptions. So this unified model composite approach is actually justifiable. And I will just briefly flash these by. You can check them out later. It actually does seem to render really useful benefits, both in terms of training speed and also generalization benefits in a contextual bandit setting. Okay. So I think that's all I want to say about the one-step decision-making problem for the time being. Maybe just briefly to step back. All we're doing here is isolating these simple problems, but digging in a bit deeper and trying to understand the nature of what algorithms make sense, what problem formulations make sense, and how we might achieve sort of empirically more effective techniques that also have some theoretical justification. I still find it quite surprising that we're still making fairly significant progress to this day on understanding this simple core problem. Nevertheless, I'm going to take this as an opportunity to kind of stretch the ambition out to the sequential decision-making context and highlight another recent piece of work where we're trying to understand something that's specifically about time and reasoning horizons beyond just simple optimization and missing data inference. Okay, so just a brief discussion of issues that arise in learning how to make decisions with sequential dependence. So here, just to re-ground the discussion, we imagine a sequential decision-making context. So a state here would be like a context in the previous discussion. So we're in some context depicted by this red node, and there's a set of actions depicted by the outgoing edges. So previously, what we'd be considering is you're in a context, you take an action and you receive a reward, here depicted, say, by a $sign. Okay. What's new, so this is exactly the contextual bandit setting. What's new here is that in addition to receiving an immediate reward for choosing that action, you wind up in another context that's directly dependent on the action that was chosen. And if we just chain a bunch of these together, we can quickly see that the consequences of that initial action choice, the most profound consequences of the initial action choice aren't the immediate reward. It's in fact the long-term reward that you're ultimately destined to achieve on a path or a sequence of decisions. So this creates a much more challenging inference and learning problem where we have to now think about the long-term consequences of decisions. But how long-term do we have to reason? And we have to learn on finite data with like finitely long trajectories, for example. To further reduce and simplify the problem, to kind of make the intuitive challenge clearer, I'm just going to assume discrete time. So this picture already shows a discrete time dynamical system. That is, there's discrete jumps from state to state. And also, I am going to consider a simpler deterministic setting. The advantage of a deterministic setting is essentially we're just walking on a directed graph. Every action is an edge on the graph, a directed edge, and every state is a node in the graph. Now, the deterministic setting does simplify the decision-making problem a great deal. In particular, we know that for a deterministic system, an open-loop decision-making strategy can be optimal. That is, from every state, you can just close your eyes and roll out a particular optimal sequence of actions and never course correct. So admittedly, it's a simplification, but it still is a challenging problem, and it allows us to focus more on a particular issue. If you're hung up on stochastic control, very interesting problem, lots to say about it. But stochastic control is also just a walk on a directed graph in the finite case, where we just have an additional player called nature who plays a stationary stochastic policy when it's their turn to move. But I'm just going to stick to the deterministic setting and focus on the issue of how do we manage the reasoning horizon when we're trying to learn how to successfully choose action sequences in a domain like this. Now, I'll try to just ground this out a little bit more concretely in a simple scenario. Another version of this deterministic sequential decision making is actually just traversing a decision tree. So another way to think about it is I give you a decision tree, you start at the root, and you can follow paths to leads. And maybe we follow a number of paths. Now, the key thing about a tree, of course, is that it's combinatorially large. So in fact, in practice, if we're thinking from a learning context, you will only ever see an infinitesimal fraction of the possible paths. You will never traverse anything like a real serious fraction of this tree. So the key issue must be extrapolation. In order to find a good path through the tree, near optimal or good or something reasonable, we quite clearly are going to need to be able to extrapolate the information we get from an infinitesimal subset of paths out to other candidate paths that we hope are significantly better. Now, quite clearly, in the worst case, we can embed arbitrarily hard problems here. We can just put a needle in a haystack, one goal, leaf, and no information in the tree, and you'll never find it except by enumeration, of course. But what we're interested in are more, more realistic problems where there's actual structure on the rewards on edges in the tree. And we want to somehow capture that structure and use it to extrapolate and make good predictions about possible rewards and paths we haven't seen yet, and use that to drive a more efficient exploration process. Okay, fine. Now, to set this up a bit, I need to just ground it one step further in the classical thinking about this kind of problem. So sort of the default thinking at some level in reinforcement learning and dynamic programming is through this concept of a value function. Now, I want to dig into this a bit because I think this forces us to commit to a couple of things we may not want to be committing to. Okay, anyway, value function. The definition is not that interesting. So in a finite, like bounded horizon setting, we could define the value of a node, say in a tree, as nothing but the maximum possible sum of a successor path from that node to a leaf. So it's literally defined by an enumeration over all outgoing paths and just accumulating rewards on the path and taking a max. Similarly, the edge value function or action value function is just defined by first committing to an edge and then maximizing overall future paths. Not very interesting. Okay, what is interesting though is a simple version of what Bellman's optimality principle looks like in this setting. And so there's many important consequences of Bellman's insight, but let me highlight some that I think are relevant to this discussion. So even though we define the concept of value in terms of this optimistic, explicit enumeration over future paths, Bellman had this really nice insight, which is the optimum values also satisfy a system of local constraints, or you could think of it as a local recursion. So here we can see that the optimum state value function defined by enumeration also satisfies a local constraint that the optimum value of a node consists of maximizing only over its immediate outgoing edges, the immediate reward on that edge, plus the optimum value function at the future from the state that you encounter. So a purely local characterization. And more significantly, it turns out that there is only one function that satisfies this constraint at every node, and it's the optimum value function defined in the first line. Similarly, for the edge value function or the action value function, we have this local consistency notion. This is very attractive, right? This means that instead of thinking about, defining these values as explicit search, we could think about trying to learn or define these values in terms of local consistencies. If you can achieve anything like a reasonable value function estimate or a value function, there is another benefit here, which is it now allows you to act completely myopically. That is, the decision-making process becomes one where the only search involved is one level deep. We can now make optimal action decisions at a node S simply by enumerating the outgoing edges and nothing more. And by referring to the immediate reward in the edge plus future value, or just the edge value function itself. So indeed, this is very attractive. We've kind of reduced search to local consistency where we can now act myopically. And this is so attractive. I think it's been an endless source of distraction in this field. It's certainly distracted me for some decades, and I think others. But I want to draw attention to an issue here, which is this is doing something rather ambitious. It's actually planning to the maximum possible horizon, but it's compiling things out so that you can act at the minimum possible horizon. So value function is full horizon, policy is the minimum possible horizon for decision making. What this means is, of course, is the value function is compiling away all future sequential search into a lookup function. And I'm gonna claim that that's asking a lot, maybe too much, in fact, in practice. So here's a proposal. What if we reconsider this, but start to think a bit more flexibly about how we're managing the reasoning horizons? And there are many reasoning horizons of interest here. There is the horizon that we're planning to, so the conceptual horizon over which we want to make optimal decisions eventually. There's the decision-making horizon, the horizon over which we're searching to choose actions. There is actually the horizon that we're using when we're learning, like when we're taking sample data and we're trying to fit a model. So there's at least these three distinct horizons, all of which are important. And unfortunately, the default way of thinking commits to very simple choices, that the planning horizon should always be the maximum horizon, the decision horizon should be the minimum horizon, and the learning horizon often is just the minimum horizon, or maybe stretched with k-step returns. Actually, I'm going to claim this is highly problematic. In fact, there are a lot of benefits to be gained by thinking more flexibly about horizons. To enable this, let me start by just proposing this slight, mild generalization of value function over edges to be what I'll call a generalized counterfactual value, which is defined on a sequence of edges or subpaths. So let's consider a notion of generalized counterfactual value, which is the value of being in a state, say, or a node S0, and then committing to a subpath of length L with edges E01 to EL-1L. And then just define what the counterfactual value is. And that definition decomposes into two parts, sort of like before, in terms of Bellman consistency. There's the explicit part, which is the explicit rewards achieved by that subpath that we observe. Followed by a recursive part, which is then completing the definition of the value in terms of an optimistic, exhaustive future search, but not to full horizon, a future search from the horizon L that we explicitly rolled out to on the subpath up to some horizon U, so U minus L. So we have a short-term horizon L that we can stretch out beyond 1, and then we have a long-term horizon U. But in principle, we can imagine setting the long-term horizon U to something less than the maximum possible horizon, which often is infinite in the definition anyway. Okay, so I'm going to try to argue that this is really beneficial, and it allows us to make progress in problems which are otherwise vexing. First observation is that if you can somehow learn or recover such a counterfactual, sort of subpath value function, it does enable a form of decision making. But now the cost of decision making is, expanded a bit by the near-term horizon L. That is, if I gave you a counterfactual value function that scores subpaths of length L, we can still use it to make decisions. How? When I'm in a state S0. I perform an horizon L search over a possible length L subpaths, evaluate each under the counterfactual value function, and take the max. And then once we've found the maximum path, we execute the first action in that path. This is isomorphic to model predictive control. Here, just counterfactual predictive control given a counterfactual value function. Okay, no big deal. Why am I making a big deal out of this? Well, I'll try to argue it shortly. But intuitively, this is actually really beneficial. First of all, in an environment that's handed to you, nobody gave you any guarantee that the episodic horizon is a reasonable one for that problem. Nobody gave you a guarantee that the clock speed, the rate at which states were sampled in the data, was a reasonable one to learn the problem. You're just handed a problem. And what I'm saying here is it makes sense to think a little bit about how we're managing these reasoning horizons. For example, why would we want a decision-making horizon bigger than one? Well, we can see examples of this everywhere in high-performance decision-making, like in game playing. If you want to beat Lee Sedol at Go, or Kasparov at chess, no one has done this, but by compiling away all search into a value function and then just doing myopic decisions from a value function. You obviously will use some search, a combination of search and compiled out value. Another way to see it is that some search reduces the complexity of the compilation process of the value function. So there really is a trade-off here. Why might we not want to reason to the maximum horizon? Well, in many problems, the maximum horizon is really long, like infinite or thousands of steps. But actually, the real decision-making problem mostly is tactical. You're playing some video game on Atari, and there is like a multi-thousand step horizon, but really you just want to shoot some aliens and hide. You just need tactical plans that are at a much shorter time scale. So in the interest of time, I'll speed up a bit on details. Maybe people can follow up with me after. But we started to take this a bit seriously and look at learning these kind of generalized counterfactual value functions and represent them in various ways. But you might think of it as simply learning a model. So if I learn a model of the dynamics and the rewards in some domain, that allows me to kind of represent counterfactual value predictions. What I want to point out, though, here is that, okay, sorry, there's a detail there, but there's an important opportunity here, and it has to do with the bootstrapping. So normally when we're learning value functions, we're actually looking for a training signal based on local consistency. And here we see, the Bellman local consistency principle written out explicitly here for us. And it just says that we want our value function to be consistent in the Bellman sense. If we could achieve exact equality everywhere, it would be the exact correct function. But here the consistency has two parts, right? There's the current value. There's the observable part on the observed rewards for, or on an explicit part on the action, the subpath. And then there's the recursive part, the self-referential part in the future. Now, the self-referential part in the future is the source of most of our training pain because this is the bootstrapping. So we could think of this as a regression problem of the left side trying to learn to approximate the right side. The problem is if we have this self-referential part on the right side, we wind up with this kind of non-stationary target. We learn the left to match the right, but then we change the right. And so we get these non-stationary targets, creates no end of headaches around training and complexity of training algorithms and stability issues and so on. One of the interesting opportunities by now thinking more flexibly about both the planning horizon and the decision-making horizon is we can think about useful alternatives like, for example, what if the planning and decision-making horizon are made equal? Well, in these kind of edge cases, we can completely eliminate the bootstrap and have a pure regression strictly to the explicit part. This turns out to be a huge benefit. Okay, so I'm getting a bit short on time, so I'm going to just kind of move along here. Maybe just to a demonstration, a more concrete way to demonstrate what I'm talking about. So, a popular kind of toy domain is pendulum, where we're trying to swing a pendulum around and stabilize it in a vertical position. Okay, why this is an interesting reinforcement learning problem is we, in addition, have a reward function which just strictly penalizes the pendulum for going around the bottom. And we can also see that there's sort of two regimes in this problem. There's kind of like a short horizon problem where you're just stabilizing it at the top, but then there's a longer horizon problem where we need to swing through the costly part of the space. Now, the problem with this swing around phase is that you're heavily penalized. So any sort of myopic reasoning about the consequences of your actions quickly tell you you don't want to swing around the bottom, but it turns out it's underactuated and you have to swing around the bottom. And the only way to successfully solve this problem is to actually have enough of a temporal commitment on an action sequence that forces you to go through the pain and to go far enough up the other side to see that it's actually beneficial. If you dare solve a problem like this in the default setup where we're planning to the maximum horizon, here 200, so we're trying to think conceptually of a 200 step action sequence, but we're deciding at the maximum frequency. Well, the problem is the action consequences at maximum frequency are so minimal, and we cannot get the sufficient commitment to go through the longer paths. So I've never been able to get anything like this close to working. You can actually visualize the optimum cost to go, reward to go value surfaces for this problem, starting with the myopic reward, ending with the true optimal value function. And we see there's very interesting structure here, but I just want to point out that somewhere in the middle, a horizon between 32 and 64 is sufficient tactically to start to see decision-making boundaries that match the long horizon decision-making boundary. So for a problem like this, it turns out that if you cannot commit or plan ahead for an action sequence of length at least 32, there's very little chance of solving this problem. So what we're able to show is just simple experiments that if you actually control these horizons up to some reasonable length 32 and eliminate bootstrapping, we get a very trivial form of regression that is actually able to solve a problem like this fairly quickly. In fact, in pendulum, it solves the problem in something like 5 or 6 trajectories. It's just a simple demo. This actually compares fairly well to even much more sophisticated, much deeper state-of-the-art approaches. In fact, it actually is able to solve the problem significantly faster, at least in these simple settings. Now, I'm not really trying to turn this into an empirical head-to-head. I think mostly I just want to conclude this by pointing out that even though Bellman's reduction is incredibly beautiful, it has distracted us and made us maybe too ambitious in the reasoning horizons that we're assuming for planning, and also maybe hasn't allowed us enough flexibility in thinking of the reasoning horizon for decision-making. Another observation is expecting tactical proficiency to emerge as a byproduct of long horizon strategic optimality. It's a nice dream, but it may be a bit naive. Another observation is if we can eliminate bootstrapping, we significantly simplify everything. So it's just a straight out regression. There's almost no hyperparameters. None of this implementation matters detail. It's a very turnkey kind of approach if you can manage the horizons. And in fact, Bellman's reduction is not the only way to achieve max horizon strategic optimality. This suggests maybe another way to think about it is more bottom up, like tactical horizon, and build that up in a hierarchical fashion to a long run strategic optimum. This is a way to more quickly get competence in a domain and build up rather than hope that eventually bucket brigading, backups will do it for you. Okay. So I know I'm running a bit out of time, but that's the end of what I wanted to say. So I just wanted to summarize by saying I just sort of gave a few case studies of fairly reductionist, like small investigations of subproblems of the overall picture. Of course, there's many more problems to understand, certainly around the exploration loops and so on. But I think at least for me, this has really helped isolate issues. And has led us to be able to find, algorithmic improvements that I think are a little bit more grounded, a little bit better connected to other areas of study, and maybe a little bit more robust. And so I hope others can join us in this pursuit. Thank you for your attention.
Fantastic. Thanks very much, Dale. That was a really fascinating talk. We are actually out of time, so I think at this point we'll stop the recording and the YouTube streaming, but we can keep the Zoom webinar going a little longer if folks want to ask questions on the Q&A. So thanks very much, Dale.
Thank you.
All right, so hopefully we've stopped the streaming. And there is a Q&A feature. If people want to ask questions, feel free to go ahead and do that in the Q&A. While they're working out how to use that, Dale, for the last part, everything depends here on the planning horizon and the horizon of the Q function. I forget what you called the
Yeah.
U horizon. So it seems like, you get a whole set of very different problems when you choose those horizons differently.
Yes.
Presumably, the right choice, like the pendulum example, is very problem specific. So is
Yes.
there, is this something that you would advocate choosing by trial and error? What's the, how do you find those sorts of?
Yeah, so I would say this particular research is still kind of in a somewhat immature state. I think clearly in pendulum, we have so much understanding of the domain that we can, pretty much eyeball reasonable like horizon choices. I mean, in the long run, of course, you'd like the horizon choices maybe to be adaptive. And you'd like to be able to formulate like what signal or feedback are you looking at that allows you to judge whether or not like your planning horizon is too long or too short, or whether or not your decision making horizon is too long or too short. I think depending on which, and I didn't have time to really emphasize the learning horizon, which is the kind of the temporal extent that the actual parameter optimization is running. I think it's a bit different in each case. I think the decision-making horizon is all about the trajectory optimization cost. In some sense, if you stretch the decision-making horizon out further, you can probably make better decisions, but the problem of finding good subpaths out to that length gets exponentially harder as you stretch the horizon out. So there's sort of a computational consideration around decision-making. In terms of the planning horizon U, that's not as much a computational issue as it is an ambition issue. It's as if like we could set out that we want to solve like Go, out to the the end of the game. Like that's a fine ambition, right? But if I'm just learning how to play Go, like really, that's what I should be trying to do, like win Go games. Like, there's a lot of sort of shorter horizon tactical like understanding and Go, like at what scale do you need to understand patterns and how they play out and so on and so forth. And I think that the ambition, if you're too ambitious, it just makes it so difficult to compile out all of that future search into your neural net, near horizon decision maker. And so I don't quite know yet what the signal is, but the intuition is something like, we should be dialing back the ambition until we're succeeding at something, and then, and then maybe stretching it out, as learning progresses.
Yeah.
So there's a lot of intuition, but I don't yet have clear technical proposals.
Yeah, I guess for the U horizon, there's also a kind of stationarity issue, right? That does, if that's short of infinite, then you do have to be concerned about where you are in the game, right?
Yeah.
What stage of the game you're at or something, right? These things are going to change.
In fact, the effective horizon is also state specific, right?
Mm-hmm.
There are going to be easy situations to be in. There are going to be hard situations to be in. Yeah.
So there's a question posted. So there are a few people that asked about a reference for the last part of the presentation. And then there was a question at the end that Abhishek asked about the escort transformation and the comparison to the more common softmax transformations and extending that to the full RL problem.
Oh, sorry, I think I have to scroll down to see more. Oh, are there some indications of those extending to RL? Yeah, I mean, we've tried it. I mean, one of the pictures I flashed by was like a 4-room, problem. It seems like it helps training a lot. I think what we've been, okay, so me personally, for that research, what I've been most distracted by is attention, like transformers and attention models that embed this attention mechanism using softmax everywhere. And you can see, if you look in those architectures, there is a scaling, like divide by in degree kind of thing there. So clearly, you know, the inventors of these techniques struggled a lot with this kind of saturation and trying to avoid, you know, premature determinism in the transfer function, and found a recipe that works. My conjecture is that if you just pull that out and plug in escort, like, you know, like training problems are going to be significantly easier. We haven't yet managed to try that out, and we are meeting some skepticism from, you know, the people who really understand and use those things. So it hasn't been that straightforward, but I actually still want to be proven wrong there. And we haven't quite gotten to that. But I think the ambition is the full one, like everywhere you use softmax. Why? And I think you will find it, at least from an optimization standpoint, it's a problematic choice. Now, whether there are detriments on the generalization side, I don't know. And some of my colleagues tell me, like, they've tried this in supervised learning and they didn't win, you know, they didn't get generalization gains. I didn't hear much of a reaction on the training costs, which I conjecture would be significantly better. So I'm not sure if, you know, if it's that consequential, but in RL, I think the training costs are so overwhelming still that maybe that would be a higher impact direction.
Mm-hmm. Right. I think all the questions that, oh no, we've just got another couple pop up. One more. Have you tried mellow max of Asadi and Littman instead of softmax?
Okay, well, I know about mellow max, so I can go that far, but no, we haven't tried it. Okay. Maybe that's a side discussion. Mellow max is maybe interesting, but I've had some conceptual difficulty. It doesn't quite give us the same duality between two spaces. Anyway, but we could follow up offline.
Right.
I think, yeah.
And the others are all about finding pointers, references to the work.
Yeah, the last 20 minutes is a to be revealed. It's actually ongoing work. Like, we're literally just pulling it together. But I thought it wouldn't be nice to have a talk without some discussion of time.
Fantastic. All right. Thanks very much, Dale. Thanks again. That was a wonderful talk. Really appreciate it.
Thank you. Thank you for hosting me, Peter. Yeah.
All right.
Bye.